So we mentioned last time we'd be tackling this problem, and I think that was the one I mentioned was out of the homework to give you some idea of where we are. But we have taken this piece of steel and bored a hole in it and put a rubber plug that just fits down in there, maybe some sort of a rubber stopper that just fits in there. And then we've maybe put a piece of steel over the top of it here so that this force doesn't punch down into the rubber. And we're applying a force there to that rubber. And you can imagine that the rubber is probably going to compress a little bit, and that's going to cause the rubber then to put some pressure on this surface. And this is actually a hole. If we were, it's round in section. So whatever is happening in the, let's say, the z direction, which is left to right in this picture, would also be happening in the y direction, which is in and out of the picture. And we're told the diameter of this bore is d, and we'd like to find the lateral pressure, whether that's the pressure in the y direction or the pressure in the z direction. We'd like to find that in the terms of the diameter d, the force F that we're applying, and Poisson's ratio for that rubber. We're not going to talk about Poisson's ratio for the steel because we're going to figure that the deformation of the rubber is much greater than the deformation of the steel. And we'll take that the steel is essentially fixed then. So let's inventory what we have if we were to go through this. If I take this as an x, y coordinate system, and I think in your homework problem they use a slightly different coordinate system. They rearrange x, y, and z. So don't let that throw you. But I'm going to take this as my x, y, and z up here. And if I talk about sigma x, I can say that that's pretty straightforward. That's in the up and down, the vertical direction here. So I could say that that's simply equal to the force divided by the area. We saw that a long time ago in class. And then if I talk about the sigma in the y direction, that's that pressure that I'm looking for. And for that matter, that would also be the sigma in the z direction. So that's what I would like to find out of this thing. If I talk about epsilon x, that's how far is this plate here going to move up and down? Well, that's hard to say. I don't really know that one. And I don't necessarily, I'm not asking for that one, so that's something I'd like to try and avoid if I could. Maybe we should talk about epsilon y, and that's where I said that we're going to take the steel as way more rigid than the rubber, so we'll take the epsilon y as equal to 0. The steel doesn't yield at all, and we can also say that's equal to epsilon z. So with that at hand, I can go and look at Hooke's law, and I'm going to use the triaxial. So the full 3D equation where we can say that epsilon y is equal to sigma y divided by Young's modulus minus Poisson's ratio over Young's modulus times sigma x plus sigma z, I think we had. When we went through those expressions, you go back in your notes and look those up, but I think that's correct. So let's put what we know into this thing. We said epsilon y, that was equal to 0, is equal to sigma y. That's going to be what? P. And it's in compression, so I'm going to say that it's negative over E, and then I'll have minus Poisson's ratio, that's for the rubber piece, over Young's modulus. And then I've got what? Sigma x. That would be what? Minus F over A, and maybe I better be careful and say that these are both compression. So if we talk about this in compression and that in compression, that's where we're getting those negative signs. Okay, so minus F over A. And then sigma z. Do we have sigma z? Yep, that was also minus P. So I can multiply both sides by E, and I will have that 0 is equal to minus P plus Poisson's ratio times F over A plus P. Multiply Poisson's ratio through, I have 0 is equal to minus P plus Poisson's ratio times F over A plus Poisson's ratio times the pressure P. I'll move the P terms to the other side, so I'll have 1 minus Poisson's ratio times P is equal to Poisson's ratio times F over A. And solving for P then, we could say that the pressure P is equal to Poisson's ratio divided by 1 minus Poisson's ratio. So I have a term there, times F over A, right? Was that a complete answer? Well, let's see, force over area, that's an appropriate unit for pressure, isn't it? And this first term would be unitless. Is there a question there?
Yeah, on the first line.
This one?
Sigma Y, or is that Z?
This one here?
No, the last one.
This one here?
Yeah.
Sigma Z? Okay. Other questions? Okay. So I think we're okay with this equation to some extent. I mean, this term here, Poisson's ratio divided by 1 minus Poisson's ratio, that's going to be unitless. And then F over A, that will have the proper units for pressure. The only thing we have to go back and read our directions. We'd like it in terms of the diameter D, the force, and Poisson's ratio for the rubber. Well, presumably the Poisson ratio that we have here is for the rubber piece. But I don't have any provision for A, so I probably need to recognize that A is going to be equal to what? Pi times the diameter squared divided by 4, right? Making that substitution, I can then come up with a final answer that we have Poisson's ratio for the rubber divided by 1 minus Poisson's ratio for the rubber piece. And then we're going to be multiplying this by the force divided by pi times that diameter squared over 4. So a bit of a technicality, but making sure that we're correct there. So that would be the pressure that's developed. This would be quite a bit more difficult problem if this was maybe a brass plug or something like that and had a stiffness that was on par with the steel. Then we'd have to start looking at the steel moving at the same time, but still very similar process. Questions with that?
That's the pressure on the wall on the outside of it.
That's the pressure that the rubber is pushing onto the steel with, and of course would then be the pressure that the steel is pushing back on the rubber with.
We wouldn't use, it would be the cross-sectional area of that rubber, it wouldn't be the total surface area around.
Yeah, if we look at a top view of this thing, the top view looks something like this, where we have this steel container and then we put that plug in there of the rubber. Other questions? Well, so we've been using Hooke's law for a little while. I'd like to now use Hooke's law again and use that to transition from Moore's circle of stress to Moore's circle of strain. So we'll talk about what Moore's circle of strain looks like. We've worked with Moore's circle of stress. So let's say that we have an object and we apply a variety of forces to this thing. We could even put some moments on there. You could have distributed loads, whatever you'd like. And we look at the strains at a particular orientation. And we wonder what happens if we change the orientation, if we look at these strains at a different orientation. So we'll go through this. I'm going to go through this fairly quick. Your author does a more thorough job of this, but just to give you a feel for a little bit what's behind there. Well, let's say that I take that this first element here, and I'll make the element, I'm going to say that this is the x direction, I'm going to say this is the y direction. And I'm going to say, well, what happens if I rotate this thing? So I'm going to rotate this over here so I now have the x prime direction, and in here I have the y prime direction, just like we did when we were talking about rotating stress. I can rotate strain. And I'm going to say that this is dx, I'm going to say this is dy, and then we'll say that this is rotated through some angle theta. And we could talk about some ds across there if we wanted to. Well, if I talk about strain in the epsilon x direction, it stretches and gets longer in the x direction, doesn't it? So this stretching or strain here would be epsilon x times dx, wouldn't it? So we could say this is due to epsilon x. And if I look at what happens on this new axis here, this x prime axis, I have this distance in here, which is given by what? Epsilon x dx. So epsilon x dx. And then I have to adjust for this angle, so I'll say that it's cosine theta. So this distance here, when I transform it to that new x prime axis, I've got epsilon x dx times cosine theta. And I could do this for the y direction, or epsilon y. So let's see what that looks like. So there's the x direction, and again there's the y direction. And I'll rotate this thing up here. There's x prime. There's y prime. And I'm going to talk about this straining in the y direction. So it gets longer here. And it could get shorter possibly. It's a little easier to think about maybe it getting longer. But we could say that this is epsilon y dy, because this is again dy, this is dx, ds across the diagonal. You could say that this angle was theta. So if I transpose that onto this direction, I have something that would be given as epsilon y dy now times what? The sine of theta? You've got the sine of theta there. And this is, of course, due to epsilon y. Now, the last thing that could cause change in the x prime direction would be gamma xy. So let's look at that one. And this will be the last picture that I draw, so we won't spend the whole day doing this. So there's our x direction, our y direction, and then let's say this is x prime and y prime, and again dx, dy. And when it strains due to gamma, the thing looks something like this, right? It strains like that, where by definition this angle in here is what? Gamma xy. So we can talk about this distance here as what? Well, it'd be gamma xy times dy, because that's just arc length, times what? Then cosine theta, isn't it? I mean, if you take this angle and you multiply it by this distance dy, that gives you the arc length that's going to give you this distance here. And then cosine theta just gives you the component in the x prime direction. So this is due to gamma xy. So let me put this all together. So I'll say total elongation in the x prime direction. So we can say that we'll call it maybe delta x prime is equal to, I'll take this piece here, epsilon x dx cosine theta, and then that piece there plus epsilon y dy sine theta, and they don't all necessarily have to be positive. I've taken them as positive, but they could be negative too. And then this piece here, plus gamma xy times dy times the cosine of theta. So I'd like to then maybe talk about the strain epsilon in the x prime direction, which would be equal to delta in the x prime direction divided by the original length. And the original length, which say was ds across there. I've labeled that on those first two drawings. So I could say that this was then epsilon x times dx divided by ds times the cosine of theta plus epsilon y dy over ds times the sine of theta plus gamma xy dy over ds cosine theta. Well, let's see. By definition, we know that, so I'm going to list a variety of things I'm going to use to simplify this. So the sine of theta, that we could really say that that is, by definition, dy ds, wouldn't it? I think so, yeah. There's theta, the sine of theta. So likewise, the cosine of theta would be equal to dx ds. That should help us. And then we're going to have a bunch of sines and cosines, so we'll have to use our trig functions here. So sine theta times cosine theta is going to give us 1/2 sine 2 theta. What else do I need? Cosine squared theta is going to be equal to 1/2 times 1 plus cosine 2 theta. And then I think the last one, I'm good because I'm running out of room, sine squared theta is equal to 1/2 1 minus cosine 2 theta. So there's kind of a trip through trig class. We'll take all of those things using these first two, and then what those create, simplifying with their trig identities, and I can reduce this expression here. So I'll apply all of those to that expression, and I'm going to get something that looks like this. So applying those, I will have that epsilon in the x prime direction is equal to 1/2 times epsilon x plus epsilon y plus epsilon x minus epsilon y over 2 times the cosine of 2 theta plus gamma xy divided by 2 times the sine of 2 theta. Okay? And that doesn't look like it was particularly helpful. You might say, well, gee, I like this form better. Well, if we were to go through this again, looking at what if we looked at gamma x prime y prime, we would go through a very similar process. I'm not going to. But I'll write down the equation. Actually, I'd need to do gamma x prime y prime divided by 2, and it'd be equal to minus 1/2 times epsilon x minus epsilon y times the sine of 2 theta plus gamma xy over 2 times the cosine of 2 theta. Let me double check, make sure I wrote those equations down right. Yeah, I think we're okay. Now, you might say, well, those look like awkward equations, but you've seen equations very similar to these. If you let epsilon x prime equal sigma x prime and epsilon y prime equal sigma y prime and gamma x prime y prime over 2 equal tau x prime y prime, you'd have the same equations. Okay, you get the same equations that we had for Moore's circle of stress. So if we use these variables, we get Moore's circle of stress. If we use these equations, we get the circle of strain. Okay. The circle of stress sounds more dastardly, but the circle of strain is important. And you might wonder, well, we're going to come up with an axis that's gamma over 2. You might wonder, well, why do we have an axis that's gamma over 2? Well, that's just the substitution to make these equations look the same. And I don't think anyone wants to use equations like this. We want to try and get that graphical tool. A graphical tool for Moore's circle of stress worked well for us. So we would like the graphical tool for Moore's circle of strain to work equally well. So let's see if we can do this. I'll talk briefly about some rules for Moore's circle of strain, which will be very similar to the rules for Moore's circle of stress. Then we'll get a problem done and show you that hopefully it's not as difficult as you might think. Certainly it's a reason for understanding Moore's circle of stress, because this is all predicated and based on, if you can do Moore's circle of stress, the transition to Moore's circle of strain is, and hopefully will be, an easy one. Well, let's do that then. So if we look at Moore's circle of strain, I think it's missing an L. So looking at Moore's circle of strain, we're going to have an axis that looks like this, where we have epsilon and we have gamma over 2. Okay. Just like we had sigma and tau, we have epsilon and gamma over 2. And just like your with Moore's circle of stress, you want to either follow my instructions to the end, or you want to follow your author's instructions to the end. You don't want to mix and match them, because I start out with a different axis. Your author will be taking gamma over 2 positive down. I take it positive up, and we'll be rotating different directions. If you don't like the gamma over 2, I'm sorry, because we both use gamma over 2. Okay, it's just which direction you take as positive. So that's your axes. Then normal strain. What was normal strain? Epsilon, right? So if we have elongation, we plot positive. That seems to make sense. If it gets shorter, we plot negative. Okay. Then shear strain. Which is gamma. And I'll say gamma, and then we'll have to divide it by 2 when we go to plot it. So that's where you can make mistakes. So always remember, this is big here, gamma over 2. So when we talk about gamma, that gets a little more confusing. It's a little harder to do. But what we do is, if you have strain that looks like this, that's positive strain. Because by definition, remember when we talked about strain, it was the angle that was measured up in here. This is your strain gamma, right? Okay, so that would be a positive angle, which would you would get by having what kind of stress? Well, stress that's like this will get you that, right? So on the x face versus the y face, what do? We're going to plot x positive. Oh, no, not x positive. X is going to tend to rotate counterclockwise, so we plot x negative, and we will plot y positive. So I look at the deformation gamma, I look at the strains that would give that to me, and I go back to my convention for Moore's circle of stress to figure out whether I plot x positive or negative. Well, what if it looks like this? It could conceivably deform in the other direction, like this, where we have a negative gamma, right? We're going to have some negative gamma in there. So that's negative. And let's see, how would we get that? We'd look at something like this, wouldn't we? These would be reversed. So when I look at the x and the y here, what are we going to have? Plot x positive. plot y negative. Does that make sense? Hopefully, and your author does this differently. That's why your author uses a different coordinate system. So either stick with your author or stick with me on that. Now, once you get through all of this, what are your rewards? What can you find on this? Well, you can find, I guess the other thing is the theta. We still have that 2 theta on the element. Is equal to theta on the circle, right? Okay, so that still holds true just like it did with Moore's circle of stress. Well, let's see. We're going to have principal strains, right? Principal strains. If I were to look at a circle that's sitting out here like this, where would those principal strains be? Well, they'd be located right there and right there, where you have no shear strain, right? So just like principal stresses where you had no shear stress, principal strains are where you have no shear strains. Okay. Then we would have maximum in-plane shear strain. Max in-plane shear strain. So again, looking at something like this, where is that going to be? Well, it's going to be located up there, isn't it? It's going to be located at the radius. Now you have to be careful of that because again, our axis is gamma over 2, so you got to take that into account. We're going to find it looking at that point there. And lastly, we might have absolute maximum shear strain. Where if we have a given situation like this, maybe we're given a circle like this, and we recognize that in the z direction we have 0, we actually have another circle, don't we? And now we need to find the radius of the largest circle. Okay. So the same things that we talked about, maximum in-plane shear stress work for strain, absolute maximum shear stress work for strain also. So the terminology can be easily converted. Well, with that, let's get started with a problem just to try and pull this all together and hopefully show that it's not as confusing as it might appear. So we'll start out with a plane strain problem. Which is to say that epsilon z is equal to gamma xz is equal to gamma yz is equal to 0. So that's what we mean by plane strain. And we're given then that epsilon x is equal to minus 400 times 10 to the minus 6. Epsilon y is equal to a positive 300 times 10 to the minus 6. And gamma xy is equal to 250 times 10 to the minus 6. Remember, these are going to be unitless, typically very small numbers. So I'd like to draw Moore's circle, and maybe if we have time, talk about what's going on at principal. But we'll concentrate on drawing Moore's circle. Okay. Which I didn't bring my pencil compass. I took that back home, a little contraption, so we'll see if we can get through this. So, in drawing Moore's circle, start with my coordinates like this. We'll say that we have epsilon, and I think I'm going to say that it's times 10 to the minus 6. We'll just take care of that so we don't have all those floating around, make it a little bit easier. And then this one is gamma over 2, and also times 10 to the minus 6, so we can work with whole numbers. So if I look at the x face, what do I have? I have minus 400, so that is definitely negative, isn't it? So I'll have 100, 200, 300, 400. So there is minus 400. And then this gamma xy, that's a positive number, isn't it? So if that's positive, what are we thinking? It probably has deformed it like this, hasn't it? Is that consistent with what I just got done talking about? Yeah, right here. Okay. So with that, if I think about that, I'm looking at an element that's going to have stresses this way to make that happen. So on the x-face, it would tend to rotate it counterclockwise, so we're going to plot this thing negative. So I need to find the point that is down here at minus 125. So there is x at minus 400 minus 125. And I say, well, where'd the 125 come from? 250 divided by 2 is equal to 125, right? So we don't want to forget about that because it's gamma over 2. So there's the x point. Then the y point is positive 300, so 100, 200, 300. So there is 300. And then on the x, or the y face, I should have positive 125. So there's my y. 300 positive and 125 positive. So then it's just a matter of putting the diameter in here, like that. We'll get a center that's somewhere there, and then drawing this circle, right? We'll see how I do without the pencil compass. Not bad. Not good, but not bad. Okay. So we can say then that the center on this thing is going to be what? 300 plus a minus 400 divided by 2, which gives me a minus 50, or we should probably always be mindful that it's minus 50 times 10 to the minus 6. Dealing with small numbers here. And then with that, I could look at this triangle over here, where I have the center point here, which we now know is minus 50, and I have this point here, which is minus 400, and I know this side is what? Minus 125. I'll just say 125 because I'm looking at the triangle. That's a right angle. So this is what? 350. So I have that the radius then is equal to the square root of 350 squared plus 125 squared, which gives me 371.6, which I should probably be mindful and say 371.6 times 10 to the minus 6. Over here we might deal with this angle. That might come in handy. We'll call that alpha. Alpha is going to equal the arc tangent of the opposite side, 125, divided by the adjacent side, 350, which is 19.65. So I'd have to rotate clockwise on the circle, 19.65. If I wanted to rotate on the element, how far would I have to rotate? About 10 degrees, right? About half of that. So remember that it's twice on the element is equal to the angle on the circle. Well, I might be interested in these principal strains, so we can talk about this one. We'll say this one is epsilon 1, and maybe I'll say that this one is epsilon 2. So if we look at those principal, I got that here. So talking about principal strains, we're going to have the center minus the radius. That would be what? the center minus the radius. We have the center here, and we subtract the radius. That would be epsilon 1. And then the center plus the radius. Center plus the radius is going to take us to epsilon 2. So let's see what that looks like then. Minus 50, and then I subtract a, 372, just to round that radius off, and we get minus 422. Here I have the center at minus 50, and I add to it 372, so I come up with 322? Yeah. So I've got then that epsilon 1 is equal to minus 422 times 10 to the minus 6, and epsilon 2 is equal to positive 322 times 10 to the minus 6. Which hopefully makes sense. We would expect this number to be something larger than 300. 322 fits the bill on this. We'd expect this number here to be something smaller than minus 400. Minus 422 seems to work out on that. Okay. Now, when we start talking about the maximum, yeah, we have enough time, the maximum in-plane shear strain. What's that going to be? Well, let's see. Where is that? I mean, on the circle, that's up there, isn't it? Actually, at this point, off of the center up there. So I could say that that's equal to what? Could I say it's equal to the radius? Yeah, I mean, from a graphical sense, it's equal to the radius. But remember, what is my axis? Gamma over 2. So maybe I should say that this is equal to that, and then we'll change this and say that gamma max is equal to 2 times the radius. Does that math work? Yeah, it does. So we could say that this is equal to 2 times that 372, which gives me 743. So I have 743 times 10 to the minus 6. So be careful with that, because you're dealing with an axis that's gamma over 2. And again, your author does this also. They just have the positive axis pointing down rather than pointing up. Okay. Now, with the stress circle, we were always talking about, well, let's see if that's maximum in plane or is that absolute maximum. If we're looking at a circle here where epsilon z is equal to 0, there's epsilon z, and we actually have these smaller circles in here like this, don't we? So this is also what? Absolute maximum, isn't it? Because we were dealing with the biggest circle already, weren't we? Well, good. That takes us to a nice stopping point. We'll talk more about this, and then we'll also talk about transferring back. How can I take this state and go to more circle of stress with it using Hooke's law? So that's where we'll go next time. Take care till then.